Find somewhere comfortable. If you are already lying down, that is exactly right. You do not need to sit up for this or concentrate or follow every word. The ideas here are soft enough to arrive on their own, without any effort from you. Just let the words come, and if some of them drift past unheard, that is perfectly fine. We are in no hurry tonight. If today was heavy, if it asked more of you than you had, then this is a place to set that down. Whatever you are carrying, you do not need to carry it through the next hour. The day is already behind you, and what is behind you can stay there for now. Tonight we are going somewhere quiet and very deep. We are going inside the atom. Not to the atom as a diagram on a classroom wall with its neat circles and arrows, but to the real thing, to the trembling, ancient, almost incomprehensibly small heart of matter itself. We are going to follow the story of how human beings, slowly and painstakingly and sometimes accidentally, came to understand that hidden inside every piece of ordinary material, a lump of coal, a glass of water, the bones of your hand resting on the pillow, there is an energy so concentrated, so patient, so vast, that a fragment of metal no larger than a fingernail contains enough of it to power a city. We will take our time. The science here is genuinely beautiful, and it deserves to be felt, not just explained. So let the words arrive slowly. Let the images form at their own pace. And if you are asleep before we reach the end, then the story will simply have done its work. It begins, as so many stories do, with something no one was looking for. In the year 1789, a German chemist named Martin Klaproth was examining a black, heavy mineral that had been found in silver mines in the ore mountains of Central Europe. The mineral was called pitchblende, a name that captured something of its character, dense, dark, slightly greasy to the touch. Klaproth dissolved it in acid and precipitated out a substance he could not identify. It was a new element. He named it uranium, after the planet Uranus, which had itself only been discovered 8 years earlier. Klaproth had no idea what he had found. He thought he was cataloguing a curiosity of chemistry. He was, in fact, holding the key to a door that would not be opened for another 150 years. Uranium sat quietly in the periodic table for most of the 19th century. It was used, rather beautifully, to make a yellow-green glass that glowed under ultraviolet light, and it colored ceramic glazes in shades of orange and amber. No one suspected it of anything more profound than that. Then, in 1895, a physicist in Würzburg named Wilhelm Röntgen was experimenting with cathode rays, streams of electrons produced inside a sealed glass tube, and noticed that a fluorescent screen on the other side of his laboratory was glowing, even though the tube was covered. Through objects that should have been opaque. He called them X-rays because he did not know what they were. The name stuck, and the discovery sent a ripple through the scientific world because it suggested that matter might be more permeable, more strange than anyone had imagined. A French physicist named Henri Becquerel heard about X-rays and wondered whether certain minerals that glowed in sunlight, phosphorescent materials, might emit something similar. He planned an experiment. He would expose uranium salts to sunlight, then place them on a photographic plate wrapped in black paper and see whether the plate was affected. He was expecting the sunlight to charge the uranium up and then the uranium to release something. But in February of 1896, the Paris sky was overcast for several days, and Becquerel put his wrapped plates and his uranium samples in a drawer to wait for better weather. When he eventually developed the plates, perhaps out of impatience, perhaps out of curiosity, he found them fogged, darkened. The uranium had exposed them even in the drawer, even without sunlight, even in the dark. This was not phosphorescence. This was something else entirely. The uranium was emitting invisible rays on its own, without any external source of energy, without any prompting. Becquerel had, almost accidentally, discovered radioactivity, though he did not yet have that word. The word came from Marie Curie. Marie Skłodowska had come from Warsaw to Paris to study physics at the Sorbonne, and she and her husband Pierre took up the mystery of Becquerel's rays with a methodical intensity that would define both their lives and, eventually, shorten them. They measured the rays not with photographs but with electrical instruments, quantifying how strongly different materials ionized the air around them, how completely they stripped electrons from nearby atoms. And they found something that deepened the mystery considerably. Pitchblende was far more radioactive than pure uranium alone could account for. Something else was in there. Something even more active. They processed tons of pitchblende, tons physically, in a leaky shed that Marie later described as a cross between a stable and a potato cellar, to isolate the source. In 1898, they announced the discovery of two new elements. One they named polonium, after Marie's homeland, which was not then a recognized country. The other they named radium, from the Latin word for ray, and the word they coined for the property these elements shared. This spontaneous, unstoppable emanation of energy was radioactivity. It was a new word for a new phenomenon, and it was precisely right. What no one yet understood was why. Why did these elements emit radiation continuously, without running down, without needing fuel? The law of conservation of energy said that energy could not come from nowhere. But here it seemed to be doing exactly that. The answer, when it came, would require a completely new picture of what an atom actually was. That picture began to form in the hands of a large, boisterous New Zealander named Ernest Rutherford, who had come to work first in Cambridge and then in Manchester. Rutherford had already established, by 1902, that radioactivity was not a surface phenomenon, but a process happening inside the atom itself. That when an atom emitted radiation, it was actually transforming into a different element. This was transmutation, the ancient dream of alchemists, happening spontaneously in every sample of uranium and radium on Earth. He won the Nobel Prize for this in 1908, and then went on to do the work that would prove even more consequential. In 1909, Rutherford set two of his students, Hans Geiger and Ernest Marsden, to fire a stream of alpha particles, which are the positively charged fragments emitted by radioactive atoms, at a sheet of gold foil so thin it was nearly transparent to light. The expectation, based on the then current model of the atom, was that the particles would pass straight through with only minor deflections. The atom was thought to be a diffuse cloud of positive charge, with electrons embedded in it like plums in a pudding. Something so spread out should barely affect a passing particle. But some of the particles bounced back, nearly straight back. Rutherford described his astonishment in a phrase that has been quoted ever since. It was as if you had fired artillery shells at tissue paper and they had come back and hit you. Most particles did pass straight through, yes. But a tiny fraction were deflected enormously, and a few rebounded almost completely. The only explanation was that almost all of the mass of the atom was concentrated in a region almost unimaginably small. A dense, compact nucleus at the center, surrounded by a vast emptiness through which the electrons moved. If the atom were the size of a cathedral, the nucleus would be a grain of rice on the floor. The rest, air, empty space. This was Rutherford's nuclear model of the atom, announced in 1911, and it changed everything. But it left a puzzle. If the nucleus was packed with positively charged protons, and protons repel each other with enormous electrical force, what was holding it together? And why were different elements different? Hydrogen had 1 proton, helium had 2, carbon had 6, uranium had 92. But the masses of these elements were not simply proportional to the number of protons. Helium was 4 times heavier than hydrogen, not twice. Something else was in the nucleus, something with mass but no charge, and for 2 decades no one could find it. James Chadwick found it in 1932. Chadwick was working in Cambridge, and he had been following a puzzling set of experiments being reported from laboratories across Europe. When beryllium was bombarded with alpha particles, it emitted a very penetrating radiation that could knock protons out of paraffin wax with considerable force. Other physicists had assumed this was gamma radiation, high-energy light, but Chadwick was suspicious. Gamma rays did not have enough momentum to do what was being observed. He ran the experiments himself, measured the energies carefully, and concluded that the radiation was in fact a stream of particles with approximately the same mass as a proton, but with no electrical charge at all. He called them neutrons, neutral particles, almost the same weight as protons, sitting alongside them in the nucleus, and their lack of charge was immediately profoundly significant. Because a neutron, carrying no electrical charge, would not be repelled by the positive charge of a nucleus. It could walk straight in, unimpeded, like a key that fits a lock no one had yet tried. The neutron was the particle the world had been waiting for, though the world did not quite know it yet. In the years that followed, physicists across Europe began firing neutrons at various elements to see what happened. Enrico Fermi, working in Rome in 1934, was particularly systematic about this. He worked his way through the periodic table, neutron by neutron, and when he reached uranium he found something strange. The bombarded uranium seemed to produce lighter elements than expected, including some that moved with the wrong energy, the wrong signature. Fermi thought and published that he had created new elements heavier than uranium, what he called transuranic elements. He may have been partly right, but something else was also happening that he did not recognize. The recognition came in December 1938 in a laboratory in Berlin. Otto Hahn and Fritz Strassmann, following up on Fermi's work, were also bombarding uranium with neutrons. Hahn was one of the finest radiochemists in the world, meticulous and careful, and when he examined what the neutrons were producing, he found, unmistakably, the chemical signature of barium, an element with roughly half the atomic number of uranium, not a slightly heavier element, not a near neighbor in the periodic table, but something from the middle of the table, something that could only be there if the uranium nucleus had somehow split in two. Hahn and Strassmann were deeply unsettled. They wrote to Lise Meitner, an Austrian physicist who had worked alongside Hahn for 30 years and had recently fled Nazi Germany for Sweden. Hahn's letter was almost apologetic. He described the barium finding as a frightful conclusion that he could not bring himself to fully believe because there seemed to be no physical mechanism by which a nucleus could simply split apart like that. Meitner, spending the Christmas holiday in a Swedish village with her nephew Otto Frisch, sat down in the snow with a piece of paper and worked it out. She had in her mind the picture of the nucleus as a liquid drop, a model that Niels Bohr had been developing, and she imagined what would happen if that drop was set wobbling by an incoming neutron. She calculated the energies. She used the relationship between mass and energy that Einstein had published in 1905. And she found that if the uranium nucleus split into two medium-sized fragments, the fragments together would be slightly lighter than the original nucleus. That missing mass, converted to energy, would account precisely for the enormous burst of energy being observed. The numbers were perfect. The picture was clear. Frisch took the idea back to Copenhagen and asked a biologist friend what the word was for a cell dividing in two. The word was fission, nuclear fission, and from that quiet winter calculation, everything else followed. To understand why fission releases energy, it helps to spend some time inside the nucleus itself, not rushing past it, but actually pausing there, in that almost impossibly small space, and feeling the tension that lives in it. The nucleus of an atom is very, very small, not small in the way a grain of sand is small, or even in the way a bacterium is small. The nucleus is small in a way that resists ordinary imagination. A typical atomic nucleus measures a few femtometers across. A femtometer is 1/millionth of 1/billionth of a meter. written out. That is a decimal point followed by 14 zeros and then a 1. The entire atom, nucleus, plus the surrounding space where electrons move is roughly 100,000 times wider than the nucleus alone. If you could somehow expand a uranium atom until its outermost electrons were as far apart as the length of a football pitch, the nucleus at the center would still be smaller than a marble. In that marble-sized space, in a uranium atom, there are 92 protons and, depending on which form of uranium we are talking about, between 143 and 146 neutrons. 235 or 238 particles packed together in a space that makes a marble look like a continent. Protons carry a positive electrical charge, and the fundamental rule of electricity, a rule that holds everywhere in the universe, from the nucleus of an atom to the poles of a magnet to the clouds of a thunderstorm, is that like charges repel each other. So 92 protons, all positively charged, all crammed into a space smaller than a marble on a football pitch, are pushing against each other with an electrical repulsion that is, by any ordinary measure, enormous. And yet they stay together. Why? The answer is the strong nuclear force. This is one of the 4 fundamental forces of nature, the 4 basic ways that particles interact with each other. Gravity, you know. Electromagnetism, the force behind light, electricity, and the repulsion between those protons, you know. The other 2 are nuclear forces, and the strong nuclear force is, as its name suggests, the most powerful of all of them. At close range, the strong force is roughly 100 times stronger than electromagnetism. It overwhelms the electrical repulsion between protons completely. But here is the crucial detail, the one that makes everything else in this story possible. The strong nuclear force acts only at extremely short range. It reaches, effectively, only about 1 femtometer. 1 femtometer. At that distance, it is overwhelming. At twice that distance, it is almost nothing. It falls off so rapidly with distance that it is essentially absent beyond the immediate neighborhood of a nucleon, the collective name for protons and neutrons together. This means that in a small nucleus, hydrogen, helium, carbon, oxygen, every proton is close enough to every other proton that the strong force between them easily overcomes the electrical repulsion. The nucleus is stable, tightly bound, settled. But as the nucleus grows larger, as you add more and more protons and neutrons, something shifts. The nucleus gets bigger. The protons on opposite sides of the nucleus are now farther apart from each other. The strong force between them weakens because it is so sensitive to distance. But the electrical repulsion does not weaken in the same way. Electromagnetism is a long-range force. It falls off with distance, yes, but much more slowly than the strong force does. So a proton on one side of a large nucleus still feels a significant electrical push from every other proton across the whole nucleus, even the ones on the far side. The result is a kind of arms race inside heavy nuclei. As the nucleus grows, the strong force struggles to keep pace with the growing electrical repulsion. It can add neutrons to help. Neutrons contribute to the strong force without adding to the electrical repulsion. And this is why heavy elements have more neutrons than protons. Uranium-238 has 92 protons but 146 neutrons, because those extra neutrons are needed to provide enough strong force glue to hold the whole thing together. But there is a limit to how much extra glue neutrons can provide. Eventually, in the heaviest elements, the nucleus reaches a state of permanent, patient tension, not quite unstable enough to fly apart immediately, but not truly settled either, always on the edge. Always, in some sense, waiting. Physicists describe this state using a model that is both simple and surprisingly accurate, the liquid drop model. Imagine the nucleus not as a rigid crystal, but as a tiny droplet of an extraordinarily dense liquid held together by surface tension. the same force that makes a water droplet round, that allows a needle to float on water if placed carefully. In a water droplet, surface tension pulls the molecules at the surface inward, keeping the drop compact and spherical. In a nucleus, the strong nuclear force plays a similar role. It holds the nucleons together, keeps the nucleus roughly spherical, resists distortion. But a water droplet can also be deformed. If you flick it, it wobbles. It stretches into an oval, then recovers. Flick it harder, and the wobble is larger. Flick it hard enough, and the droplet elongates so much that the narrow neck in the middle grows too thin. The surface tension there cannot hold, and the droplet pinches off into two smaller drops. The nucleus of uranium-235 is a droplet like this, but a droplet that is already under considerable internal pressure. The electrical repulsion between its 92 protons is constantly pushing outward, constantly trying to elongate and deform the nucleus. The strong force is constantly pushing back, keeping it spherical. The two are very nearly balanced, which is why uranium-235 is stable enough to exist. Its half-life, the time it takes for half of a given sample to decay spontaneously, is about 700 million years. Long enough to be found in the Earth today, even though it was forged in a dying star long before our solar system formed. But the balance is delicate. The nucleus is not serene, it is trembling. It is a droplet on the very edge of distortion, held in shape by a force that is only barely winning against the force trying to pull it apart. And this is why a single neutron arriving from outside can tip everything. There is something else worth understanding about the nucleus, something that goes a little deeper than the liquid drop picture. The protons and neutrons inside the nucleus are not, themselves, truly fundamental particles. Each proton and each neutron is made of smaller particles called quarks. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. The strong nuclear force that holds the nucleus together is actually a residual effect of the force that holds the quarks together inside each proton and neutron, a kind of overflow, a leakage of an even more fundamental interaction. The force between quarks is mediated by particles called gluons, and the strong nuclear force that acts between protons and neutrons is, in a sense, the gluon field leaking out through the boundaries of each nucleon and reaching across to its neighbors. This is deeper than we need to go tonight, and you do not need to hold it all. But it is worth knowing that the story goes further down than the nucleus, that beneath the proton and the neutron there are layers still, and that the force holding it all together has roots that reach into the very fabric of matter. The nucleus is not the bottom. It is just the level at which the energy we are interested in lies. For now, hold the image of that trembling liquid drop, 92 protons, 143 neutrons, packed into a space smaller than a marble on a football pitch, held together by a force that is almost, but not quite, winning. That image will carry us through everything that follows. Picture a neutron. It has no charge. It has no color, no smell, no quality that would announce its presence. It is slightly heavier than a proton, about 1 part in 1,000 heavier, and it is, in isolation, unstable. A free neutron left to itself will decay into a proton, an electron, and a third particle called an antineutrino with a half-life of about 10 minutes. But in the context of a nuclear reactor, 10 minutes is an eternity. The neutron we are following tonight is what physicists call a thermal neutron. The word thermal here means that the neutron's energy is roughly in equilibrium with the thermal energy of its surroundings, the energy of ordinary warmth. A thermal neutron moves at somewhere around 2 kilometers per second. That sounds fast, and in everyday terms it is. It would cross a football pitch in a fraction of a millisecond. But on the scale of atomic physics, it is almost leisurely. The electrons whipping around the outside of a uranium atom are moving at speeds that are a significant fraction of the speed of light. The thermal neutron, by comparison, is moving at a brisk walk. This slowness turns out to be essential, and understanding why requires thinking about what happens when a neutron approaches a nucleus. When our neutron drifts close to a uranium-235 nucleus, it does not need to push through any electrical barrier. Protons repel other protons and other positive charges. Electrons repel other electrons. But a neutron, being electrically neutral, feels no such push. It approaches the nucleus as if the electrical force did not exist, and when it comes within range of the strong nuclear force, within about 1 femtometer, it is pulled in, absorbed. Now, why does the speed of the neutron matter? The answer lies in something called the cross-section of the nucleus, a measure of how likely a nucleus is to absorb a passing neutron. This is not the physical size of the nucleus, but something more like its effective size for the purpose of capturing neutrons. And for uranium-235, the cross-section for thermal neutrons is enormously larger than the cross-section for fast neutrons. A slow neutron is hundreds of times more likely to be absorbed by a uranium-235 nucleus than a fast one. The reason has to do with the quantum mechanical nature of the neutron. When the neutron moves slowly, it has a longer wavelength, and a longer wavelength means it effectively presents a larger target to the nucleus. It spreads out in a quantum sense, and the nucleus has a much easier time catching it. This is why slowing neutrons down is so important in a nuclear reactor, and we will come back to that. For now, follow our neutron as it is absorbed. The moment the neutron is captured by the uranium-235 nucleus, the nucleus becomes uranium-236. This is not a stable isotope of uranium. It is an excited, agitated, highly energized state that exists for an almost unimaginably brief time. The energy comes from two sources, the kinetic energy of the incoming neutron and something called the binding energy of the new neutron bolts, the energy released as the neutron is incorporated into the nucleus and bonds with its neighbors through the strong force. Together, these two contributions give the uranium-236 nucleus about 6 million electron volts of excitation energy. An electron volt is a very small unit, the energy gained by a single electron moving through a 1 volt potential difference, but 6 million of them concentrated in a nucleus is enough to set that liquid drop wobbling violently. Here is where the liquid drop picture becomes vivid. The excited uranium-236 nucleus begins to deform. It stretches from a sphere into an oval, then into something more elongated still. As it elongates, the strong nuclear force, which, remember, acts only at very close range, begins to weaken across the growing distance between the two ends. The protons in one end of the elongating nucleus are now slightly farther from the protons in the other end, and the strong force between them has dropped. But the electrical repulsion has not dropped nearly as much. The long-range electrical push is still there, still driving the two ends apart. The nucleus elongates further. The middle, the neck connecting the two bulging ends, grows thinner. The strong force across that neck weakens still more. The electrical repulsion keeps pushing. And now the nucleus has reached what physicists call the fission barrier, a critical point of no return. The fission barrier is the energy threshold that separates a nucleus that will wobble and recover from a nucleus that will split. Below the barrier, the restoring force of the strong nuclear force is still strong enough to pull the nucleus back into a sphere. Above the barrier, the electrical repulsion wins. The neck snaps, and fission is inevitable. The excitation energy given to uranium-236 by the incoming neutron, those 6 million electron volts, is just enough to push the nucleus over this barrier. Not by much, just enough. The neck snaps. The nucleus divides. What emerges from the division is not always the same pair of fragments. Nuclear fission is probabilistic. It does not always produce the same products, but there are patterns. Common results include barium and krypton, or xenon and strontium, or various other pairs of medium-weight nuclei. Each fragment carries a large number of neutrons, more neutrons than a stable medium-weight nucleus needs, and so each fragment is itself radioactive and will decay further over time, emitting more radiation as it settles towards stability. But crucially, in the moment of fission, 2 or 3 free neutrons are also released. Prompt neutrons, they are called, because they come out almost immediately, within tiny fractions of a second of the split. These are the neutrons that make a chain reaction possible. Think about what this means. 1 neutron goes in, 2 or 3 come out. If each of those neutrons goes on to strike another uranium-235 nucleus and cause another fission, and each of those fissions releases 2 or 3 more, and so on, the number of fissions grows exponentially. In an uncontrolled situation, this growth is extraordinarily fast. In a bomb, it is over in microseconds. In a reactor, the goal is to control it so that exactly 1 neutron from each fission goes on to cause another fission, and the reaction proceeds at a steady, sustained rate. For a chain reaction to sustain itself, the amount of fissile material present has to exceed a certain minimum. This minimum is called the critical mass. The concept is straightforward. If the piece of uranium is too small, too many of the neutrons released in each fission will escape through the surface before they can strike another nucleus. The chain reaction will fizzle out. But if the piece is large enough, if the surface area is small relative to the volume, so that most neutrons encounter another nucleus before reaching the edge, then the chain reaction can sustain itself. The critical mass of uranium-235 depends on its shape and purity, but for a bare sphere of pure uranium-235, it is roughly 52 kilograms. Surrounded by a material that reflects neutrons back in, it can be considerably less. In a reactor, the situation is carefully managed so the chain reaction stays controlled. The fission neutrons that emerge are fast. They are moving at speeds that are a significant fraction of the speed of light, far faster than our thermal neutron was, and fast neutrons are much less effective at triggering further fission in uranium-235. So the reactor includes a moderator, a material designed to slow the neutrons down to thermal speeds without absorbing too many of them. Water is an excellent moderator. The hydrogen nuclei in water molecules are almost exactly the same mass as a neutron, and when a fast neutron collides with a hydrogen nucleus, it transfers its energy very efficiently, the way a billiard ball transfers momentum to an identical ball it strikes head-on. After dozens of such collisions, a fast neutron slows to thermal speed, ready to trigger another fission. The chain reaction, then, is not a single event, but a continuous, self-sustaining pulse of fissions, each one releasing energy, each one releasing neutrons that go on to trigger more. The reactor is a machine for keeping this pulse steady, for harvesting the energy it produces, and for preventing it from growing beyond control. But where does the energy actually come from? We have seen the mechanism, the wobble, the elongation, the snap, the fragments flying apart. We have not yet asked the deepest question: why does splitting the nucleus release energy at all? Weigh the uranium-235 nucleus before the fission, weigh the incoming neutron, add those two numbers together with the most precise instruments available to science. Now weigh the fission products, the 2 medium-weight nuclei, the 2 or 3 free neutrons, everything that came out of the reaction. Add those together. The second number is smaller than the first, not by much, by less than 1/10 of 1%. If you started with 1,000 grams of uranium-235, the products would weigh something like 999 grams, a gram, perhaps slightly less, a sliver, and that sliver has not gone anywhere. It has not been lost or destroyed or hidden. It has become energy. This is the mass defect, and it is the central fact of nuclear energy, the thing from which everything else follows. To understand why this happens, you need to think about what it means for particles to be bound together. When protons and neutrons are bound inside a nucleus, they are in a lower energy state than they would be if they were separated and floating free. This is exactly analogous to a ball sitting at the bottom of a bowl. The ball has less energy than it would have if you lifted it to the rim. To separate the protons and neutrons in a nucleus, to pull them apart against the strong nuclear force, you would have to put energy in. That energy is called the binding energy of the nucleus. Now here is the key insight. Because the particles in a bound nucleus are in a lower energy state, they also have less mass than they would if they were free. But at the level of the nucleus, mass and energy are not separate things. They are two faces of the same thing, and they can be exchanged. A system with less energy has less mass. A system with more energy has more mass, always, without exception. The relationship between mass and energy is described by the most famous equation in physics. It says that energy equals mass multiplied by a constant, and that constant is the speed of light multiplied by itself, the speed of light squared. The speed of light is about 300 million meters per second. Squaring that number gives approximately 90 quadrillion, 90,000 million in units of meters squared per second squared. This is the conversion factor between mass and energy, and it is enormous. Even a tiny amount of mass multiplied by this number becomes a very large amount of energy. Let us be concrete about the scale. When uranium-235 undergoes fission, the mass defect, the mass that becomes energy, is about 350 millionths of a billionth of a gram per atom. Written as a fraction of the original mass, it is roughly 0.9%. Barely anything. A rounding error by most standards. But multiplied by the square of the speed of light, that tiny sliver of mass becomes approximately 200 million electron volts of energy. And an electron volt, while a very small unit, adds up fast when you are dealing with atoms. To make this tangible, burning a single carbon atom in air, the chemical reaction that releases energy when coal or wood burns releases about 4 electron volts of energy. A single fission event releases about 200 million electron volts, that is 50 million times more energy per atom, 50 million. From a fragment of mass so small it cannot be weighed by any ordinary means, only inferred from the difference between very precise atomic measurements. Scale this up to something you can hold in your hand. A single uranium fuel pellet, the kind used in a nuclear power station, is a small ceramic cylinder roughly the size of the tip of your finger, about 1 centimeter across and 1 centimeter tall. It weighs roughly 10 grams. That pellet, when fully fissioned, releases approximately the same amount of energy as burning 800 kilograms of coal, or 500 liters of oil, or 450 cubic meters of natural gas. The pellet does not look different from a piece of chalk. It is not hot to the touch. It contains, locked inside the nuclei of its uranium atoms, an energy that is almost beyond ordinary comprehension. And that energy comes entirely from the conversion of a sliver of mass, a sliver that represents less than 0.1% of the pellet's total weight, into something else. It is worth pausing here on the word becomes. The mass does not disappear in the sense of ceasing to exist. It does not evaporate or dissolve. It transforms. It becomes kinetic energy, the energy of motion of the flying fission fragments. It becomes gamma radiation, high-energy light. These are not separate from mass. They are mass expressed differently. The universe's accounting is perfect. Nothing is lost. What was matter is now motion, now light, now heat. The ledger balances, but the entries have changed form. This transformation, matter into energy, is not unique to nuclear fission. It happens in radioactive decay, in nuclear fusion, in certain particle physics processes. Whenever particles are bound together more tightly than they were before, some mass becomes energy. Whenever they are separated into a less tightly bound state, energy becomes mass. The universe is constantly making these exchanges at every scale, in every star, in every radioactive mineral, in the slow decay of atoms in the rock beneath your feet. What makes fission distinctive is the scale of the exchange relative to the quantity of matter involved. Chemical reactions, burning, rusting, dissolving, also involve changes in binding energy and therefore also involve tiny changes in mass. But the changes are so small that they are completely undetectable by any instrument we have. In chemical reactions, the electrons are rearranging and the energies involved are measured in electron volts, single-digit electron volts. In nuclear reactions, the nucleons are rearranging and the energies are millions of times larger. The mass change is still tiny, as a fraction of the whole, but it is large enough to be measurable, and the energy it represents is large enough to boil water, to drive turbines, to light cities. There is something quietly astonishing about the fact that this understanding, this equivalence of mass and energy, came before anyone had split an atom, before anyone had built a reactor, before anyone had even imagined that fission was possible. Albert Einstein published his special theory of relativity in 1905, and the mass-energy equivalence followed directly from it. He was not thinking about nuclear reactors. He was thinking about the nature of space and time, about what happens to measurements of length and duration when observers are moving relative to each other. The mass-energy relationship was a consequence of that thinking, almost a footnote. It took 30 years for the world to discover a context in which the footnote became the headline. And when it did, when Lise Meitner sat in the snow in Sweden in December 1938 and applied Einstein's relationship to Hans' barium finding, the numbers came out exactly right. The mass defect of uranium fission multiplied by the square of the speed of light gave precisely the energy being observed in the laboratory. The equation was not a theory to be tested. It was a key that fit the lock perfectly, the first time it was tried. The sliver of missing mass, the vast constant, the energy that lights cities, all of it follows from a single, quiet, beautiful relationship between two things that we used to think were completely separate. Mass and energy are not separate. They never were. We simply did not know it until a man in a patent office in Bern worked it out from first principles in 1905, 33 years before anyone split an atom. The fission has happened. The nucleus has split. The fragments are flying apart at roughly 3% of the speed of light, 9 million meters per second, which is fast enough to cross the entire diameter of the Earth in a little over a second. The neutrons have been released. The gamma rays, pulses of high energy, electromagnetic radiation, the most energetic form of light, are radiating outward, and now the energy has to go somewhere. It does not stay where it is. Energy, in all its forms, seeks to spread and equalize. And the first thing the flying fission fragments do is collide with the atoms around them. In a nuclear reactor, the fissile uranium is contained in fuel rods, long, thin cylinders of ceramic uranium dioxide stacked inside a tube of zirconium metal alloy. These fuel rods are surrounded by water. The flying fission fragments, which carry roughly 85% of the total energy released in fission, shoot outward from the split nucleus and almost immediately, within a distance of a few micrometers, a few thousandths of a millimeter, slam into neighboring uranium atoms in the ceramic. Each collision transfers some kinetic energy. The fragment slows a little. The struck atom speeds up a little, and then that atom collides with its neighbors, and they with theirs. The kinetic energy of one flying fragment cascades outward through thousands and then millions of collisions, spreading from atom to atom in the ceramic until what began as the directed flight of two fission fragments has become the random, jostling, omnidirectional motion of countless atoms, and random, omnidirectional atomic motion is heat. The fuel rods get hot, very hot. The ceramic uranium dioxide in the center of a reactor fuel rod reaches temperatures of around 1,500 degrees Celsius during normal operation. The outer surface of the rod is cooler because heat flows outward through the ceramic toward the water surrounding the rod, and water carries heat away efficiently. The water in a pressurized water reactor, the most common type of reactor in the world, is kept under very high pressure, roughly 150 times atmospheric pressure. At this pressure, water does not boil until it reaches about 340 degrees Celsius, well above the normal boiling point of 100 degrees. So the water in the reactor core remains liquid even though it is extremely hot. It circulates through the core, absorbing heat from the fuel rods, and then flows out to a heat exchanger, a device where the hot pressurized water transfers its heat to a second loop of water, which is at lower pressure and which therefore boils and becomes steam. The steam then does what steam has done in engines for 3 centuries. It expands. It rushes through a turbine, a wheel fitted with precisely shaped blades, and the force of the expanding steam pushes the blades around. And the turbine is connected by a shaft to a generator, a large machine in which a coil of wire rotates inside a magnetic field. As the wire rotates, the changing magnetic field induces an electric current in the wire. The current flows out through cables into the grid, and from the grid into homes, hospitals, factories, and the small glowing screen you may have set down beside you tonight. The chain of transformation is long, but each step is physical and clear. The mass defect of uranium becomes kinetic energy of fission fragments. Kinetic energy of fragments becomes heat in the ceramic fuel. Heat in the ceramic becomes heat in the water. Heat in the water becomes steam. Steam becomes rotation. Rotation becomes electricity. The light in your room, if it comes from a nuclear power station, is the distant descendant of a sliver of matter that ceased to be matter inside a fuel rod, perhaps 100 kilometers away, perhaps more. The gamma rays released during fission and during the subsequent radioactive decay of fission products carry the remaining energy, roughly 5% of the total. And these too eventually become heat, absorbed by the water and the steel and concrete structures of the reactor. Nothing is wasted. The reactor is extraordinarily efficient at converting fission energy into heat, because the fission fragments cannot travel far and the gamma rays are absorbed within the structure. Almost all of the energy released inside the reactor core stays inside the reactor core and becomes heat. Now, to keep this process controlled, to prevent the chain reaction from growing faster and faster until it overwhelms the cooling system, the reactor uses 2 key mechanisms. The first is the moderator, which we have already met. The water that surrounds the fuel rods slows the fast neutrons released in fission to thermal speeds, making them effective at triggering further fission. But water also absorbs some neutrons. If the water temperature rises, if the reactor begins to run too hot, some of the water turns to steam, and steam is a much less effective moderator than liquid water. Fewer neutrons are slowed to thermal speed, fewer fissions occur, the reactor naturally cools down. This is called a negative temperature coefficient of reactivity, and it is a built-in passive safety feature of water. Moderated reactors, the hotter they get, the less reactive they become. The second mechanism is the control rods. These are long rods made of materials, boron or hafnium or silver, indium cadmium alloys, that absorb neutrons very readily without themselves fissioning. When the control rods are pushed into the reactor core, they soak up neutrons and slow the chain reaction. When they are pulled out, more neutrons are available to trigger fission and the reaction speeds up. By adjusting the position of the control rods, operators can tune the reactor's output with considerable precision, raising or lowering the power level to match demand. A reactor that has been shut down, control rods fully inserted, chain reaction stopped, does not immediately stop producing heat. This is one of the subtler and more important facts about nuclear power. The fission products created during operation are themselves radioactive. They are unstable nuclei, carrying too many neutrons for their size, and they decay over hours and days and years, emitting beta particles and gamma rays as they do. This decay heat amounts to roughly 7% of the reactor's full operating power immediately after shutdown, dropping to about 1% after an hour and continuing to decline slowly after that. It is not very much compared to the full power of the reactor, but it is not nothing, and it must be managed. The cooling systems of a reactor must continue to circulate water past the fuel rods even after the chain reaction has stopped to carry away this decay heat and prevent the fuel from overheating. This is the detail that makes nuclear safety engineering so demanding. A reactor does not simply turn off cleanly, the way a gas burner does when you close the valve. It continues to produce heat, less and less of it, but persistently, for days after shutdown, driven by the slow decay of fission products. The cooling systems must be maintained through this period, and ensuring that cooling is available under all circumstances, including loss of power, is the central challenge of reactor safety design. Modern reactor designs address this with passive cooling systems that rely not on pumps and electricity, but on gravity and natural convection, on the simple fact that hot water rises and cool water falls. If the pumps fail and the power goes out, the water in a passively cooled reactor continues to circulate on its own, driven by the temperature difference between the hot core and the cooler water above and around it. No electricity required, no human action required. The thick concrete and steel of the reactor vessel and the surrounding containment building serve a different purpose. They absorb the gamma radiation that would otherwise escape into the environment. Concrete is an effective radiation shield because it is dense and contains significant amounts of hydrogen, which absorbs gamma rays efficiently. The containment building around a modern reactor is typically made of reinforced concrete more than a meter thick, capable of absorbing the radiation from the core, and also of containing any steam or radioactive material that might be released in an accident. All of this, the moderator, the control rods, the passive cooling, the containment, is engineering built around a single physical reality, that the energy released when a sliver of mass becomes something else is real and substantial and must be treated with care. In the early 1970s, scientists at a uranium enrichment facility in France noticed something peculiar in a batch of uranium ore that had arrived from a mine in Gabon, a country on the west coast of Central Africa. The ore came from a place called Oklo. When uranium is mined and processed, it has a characteristic isotopic composition. Natural uranium contains two main forms, or isotopes, uranium-238, which makes up about 99.3% of all natural uranium, and uranium-235, which makes up the remaining 0.7%. This ratio is remarkably consistent wherever uranium is found on Earth, in Africa, in Canada, in Australia, in the rocks of the ocean floor. It is the same because uranium was formed in the same stellar explosions billions of years ago and has been decaying at known rates ever since. The ratio is a kind of timestamp, a consequence of radioactive half-lives that have been measured with great precision. But the uranium from Oklo was wrong. The proportion of uranium-235 was lower than it should have been, not by much, by a fraction of a percent. But the difference was real and reproducible, and the French scientists could not explain it. What they eventually concluded, after considerable analysis, was remarkable. The uranium at Oklo had already been through a nuclear chain reaction. The uranium-235 had been partially consumed, used up in fission events, before the ore was ever mined. The mine was not just a deposit of uranium. It was the remnant of a natural nuclear reactor that had operated intermittently for hundreds of thousands of years, roughly 2 billion years ago. The conditions that made this possible were very specific, and understanding them deepens the understanding of criticality that we have been building. For a chain reaction to be self-sustaining, three things must be in place: enough fissile material, a moderator to slow the neutrons, and a geometry that prevents too many neutrons from escaping before they can trigger further fission. At Oklo, 2 billion years ago, the first condition was met in a way it could not be met today. Uranium-235 and uranium-238 both decay over time, but they decay at very different rates. Uranium-235 has a half-life of about 700 million years, while uranium-238 has a half-life of about 4.5 billion years, while uranium-238 has a half-life of about 4.5 billion years. This means that uranium-235 decays much faster. Going back 2 billion years, uranium-235 was more abundant relative to uranium-238 than it is today, not by a dramatic amount, but enough. 2 billion years ago, natural uranium was about 3% uranium-235, compared to the 0.7% we find today. 3% is close to the enrichment level used in modern power reactor fuel. Nature, in other words, provided enriched uranium for free simply because the Earth was younger. The second condition, the moderator, was provided by groundwater. The Oklo uranium deposit was porous and water percolated through it. Water, as we have seen, is an excellent moderator. It slows fast neutrons to thermal speeds without absorbing too many of them. The water in the rock was doing exactly what the water in a modern reactor does, slowing the fission neutrons to the speed at which they could efficiently trigger further fission in uranium-235. The third condition, geometry, was met by the shape and concentration of the ore body. The uranium was concentrated enough, and the deposit was large enough that neutrons released in fission had a good chance of being slowed by the water and absorbed by another uranium-235 nucleus before escaping through the edges of the deposit. And so the chain reaction started, on its own, with no human intervention, no engineering, no design. The physics simply took over because the conditions were right. The reactor did not run continuously. There is evidence that it operated in pulses, cycling on and off with a period of roughly 3 hours. The mechanism for this cycling is elegant and almost playful. When the chain reaction was running, the heat it produced boiled the groundwater in the ore. Steam is a much less effective moderator than liquid water. With the moderator removed, the chain reaction slowed and stopped. The rock cooled, the steam condensed back to liquid water. The moderator returned. The chain reaction started again. The Oklo reactor was regulating itself naturally through the same negative temperature coefficient that modern water-cooled reactors rely on. It was breathing, in a sense, inhaling water to start, exhaling steam to stop, inhaling again when cool enough. This went on, with interruptions, for somewhere between 100,000 and 300,000 years. The total energy released over that time was enormous, comparable, by some estimates, to the output of a modern reactor over several years. But it was spread over such a vast time that no one on Earth would have noticed, even if there had been anyone to notice. The heat dissipated into the surrounding rock. The fission products were locked into the minerals of the ore body. The chain reaction eventually stopped, not because anything broke or failed, but because enough uranium-235 had been consumed that the deposit could no longer sustain criticality. What the Oklo reactors left behind is, in itself, deeply interesting. The fission products, the medium-weight nuclei created by 2 billion years of uranium splitting, are still there, locked in the rock, and they have barely moved. Plutonium, which was also created at Oklo through neutron capture by uranium-238, and which is one of the most concerning products of nuclear reactions from a waste management perspective, has been found only within about 10 meters of where it was created, despite 2 billion years of geological time. Other fission products have migrated only slightly further. The rock, The clay minerals in the surrounding geology have acted as an extraordinarily effective barrier, holding the radioactive material in place through billions of years of groundwater flow, tectonic movement, and the slow processes of geological change. This is not a trivial finding. One of the central concerns about nuclear waste is whether it can be safely contained over very long timescales, thousands or tens of thousands of years. The reactors provide a natural experiment run over 2 billion years, and the result is that stable geology does, in fact, contain radioactive material very effectively. The fission products did not migrate into the water table. They did not disperse through the environment. They stayed put, held by the same geochemical processes that engineers now design into deep geological repositories for nuclear waste. The reactors are a reminder that nuclear fission is not a human invention. It is a natural process, one that the universe was already performing long before there were eyes to observe it or minds to understand it. We did not create the chain reaction. We discovered it, and then, with considerable effort and ingenuity, learned to control it. There is something quietly reassuring about that. The physics does not belong to us. We are borrowing it, carefully, from a universe that has been running these reactions for billions of years. Everything we have discussed so far, the splitting of uranium, the release of energy, the conversion of mass, can be understood more deeply if we step back and look at a single curve. It is a graph that physicists draw, and it is one of the most illuminating pictures in all of science. Along the bottom axis, you mark the number of protons and neutrons in a nucleus, from 1 for hydrogen up to 238 for uranium. Along the vertical axis, you mark something called the binding energy per nucleon, the amount of energy per proton or neutron that holds the nucleus together. The curve rises steeply from hydrogen, peaks somewhere in the middle of the periodic table, and then falls away gradually toward the heavy elements. The peak, the most tightly bound nuclei in nature, occurs around iron and nickel at around 56 to 62 nucleons. What this curve is telling you is that nuclei near the middle of the periodic table are in the most stable, most tightly bound state. They have given up the most energy to binding, and they have the least energy available to release. They are, in a sense, at the bottom of the energy valley, the most settled state that nuclear matter can reach. Nuclei on either side of this peak, either very light ones like hydrogen and helium, or very heavy ones like uranium and plutonium, are higher up the slope. They are less tightly bound per nucleon, and this means they have energy to give up if they can find a path toward the middle of the curve. For the heavy nuclei, the path is fission, split into 2 medium-weight fragments, both of which sit lower on the curve, both of which are more tightly bound per nucleon than the original heavy nucleus. The difference in binding energy per nucleon, multiplied by the number of nucleons involved, is the energy released. This is exactly the mass defect we explored earlier, seen from a different angle. The fission products are more tightly bound, they have given up more mass to binding energy, and the difference appears as the kinetic energy of the fragments and the gamma radiation. For the light nuclei, the path is fusion. Combine 2 light nuclei into a heavier one that sits higher on the binding energy curve, closer to the peak. The combined nucleus is more tightly bound per nucleon than the 2 separate ones were, and again the difference appears as released energy. Fusion releases more energy per kilogram of fuel than fission does, considerably more. The fusion of hydrogen into helium releases roughly 4 times as much energy per kilogram as the fission of uranium. And the fuel... The sun is a fusion reactor. It has been one for about 4.5 billion years, and it will continue to be one for roughly another 5 billion. Inside the sun's core, where the temperature reaches about 15 million degrees Celsius and the pressure is 340 billion times atmospheric pressure, hydrogen nuclei, bare protons, are moving fast enough and are packed tightly enough that they can collide with sufficient force to overcome their electrical repulsion and come within range of the strong nuclear force. The fusion process in the Sun is not a single reaction, but a sequence called the proton-proton chain. Two protons fuse to form a nucleus of deuterium, a form of hydrogen with one proton and one neutron, releasing a positron, which is an antimatter electron, and a neutrino, which is a nearly massless particle that passes through almost everything. The deuterium then fuses with another proton to form helium-3, a light form of helium with two protons and one neutron, releasing a gamma ray. Two helium-3 nuclei then fuse to form helium-4, ordinary helium with two protons and two neutrons, releasing two protons back into the mix to start the cycle again. The net result of this chain is that four protons become one helium-4 nucleus. The helium-4 nucleus is slightly lighter than the four protons combined, by about 0.7% of the total mass. That 0.7% multiplied by the square of the speed of light is the energy that the Sun radiates. Every second, the Sun converts about 4 million tons of mass into energy through this process. 4 million tons every second. And it has been doing so for 4.5 billion years. The light that reaches your face on a warm day has traveled 8 minutes from the Sun. It left the Sun's surface as photons, particles of light, but the energy those photons carry began as mass, converted in the core of the Sun through the same fundamental relationship that underlies nuclear fission. The warmth on your skin is the distant echo of hydrogen nuclei fusing under incomprehensible pressure 150 million kilometers away. For decades, physicists dreamed of replicating this process on Earth, not in the gentle, slow way the Sun does it, held together by gravity over billions of years, but in a controlled laboratory setting where the energy released could be harnessed for human use. To fuse hydrogen nuclei, you need to heat them to temperatures of tens of millions of degrees, hot enough that the thermal energy of the particles is sufficient to overcome their electrical repulsion and bring them close enough for the strong force to take hold. At those temperatures, matter is in a state called plasma, a gas so hot that the electrons have been stripped away from the nuclei, leaving a sea of bare, charged particles. Containing a plasma that hot is extraordinarily difficult, because no solid material can touch it without being instantly vaporized. The two main approaches are magnetic confinement, using powerful magnetic fields to hold the plasma away from any solid surface in a donut-shaped vessel called a tokamak, and inertial confinement, in which a tiny target of fusion fuel is compressed and heated so rapidly by powerful lasers that fusion occurs before the plasma has time to expand and cool. For many years, fusion research produced reactions that released less energy than was put in to start them. The plasma was always losing heat faster than the fusion reactions could generate it. But then, in December 2022, at the National Ignition Facility in California, something changed. The National Ignition Facility uses 192 powerful lasers, all focused simultaneously on a target smaller than a peppercorn. A tiny capsule containing a mixture of deuterium and tritium, two heavy forms of hydrogen. The lasers deliver their energy in a precisely timed pulse, compressing and heating the capsule so rapidly that the fuel at the center reaches temperatures and pressures comparable to those inside a star. The compression is so extreme that the fuel briefly achieves what is called ignition, a state where the fusion reactions generate enough heat to sustain themselves, without needing further energy from the lasers. In December 2022, the lasers delivered about 2.1 megajoules of energy to the target. The fusion reactions produced about 3.15 megajoules, more energy out than in. For the first time in a laboratory, a fusion reaction had achieved net energy gain, what physicists call ignition, in the sense that the reaction was generating more energy than it consumed. The people in the room that night described a feeling of quiet disbelief, followed by something that took a little while to name. It was not triumph exactly. It was more like the feeling of arriving somewhere that you had been walking toward for a very long time and finding that it was real. The result has since been reproduced and improved upon. The path to commercial fusion power is still long. There are enormous engineering challenges between a laboratory ignition and a power plant feeding electricity to a grid, but the fundamental physics has been demonstrated. The sun's process can be replicated on Earth. The curve of binding energy runs in both directions, and we have now taken a step in each. The binding energy curve is, in the end, a map of where the energy and matter lives. Heavy nuclei like uranium sit on the right slope, and they release energy by rolling down toward the peak. Light nuclei like hydrogen sit on the left slope, and they release energy by climbing up toward it. The peak, iron, nickel, is the point of maximum stability, the place where nuclear matter has given up all it can give. Between the two slopes, the curve traces the shape of the energy available in the universe, patient and ancient, waiting to be understood. We have come a long way tonight. From a German chemist's dark mineral in 1789, through accidental photographs and leaky sheds and Christmas calculations in the snow, through the trembling liquid drop and the vanishing sliver of mass, through the chain reaction and the steam and the spinning turbine, through the ancient reactors of Gabon and the burning heart of the sun. It is a long journey to have made while lying still in the dark. And now, in this final stretch, we can let the pace slow further. We do not need to cover more ground. We can simply rest in what we have found. There is a hum to nuclear energy that most people never hear. Not a literal hum. Nuclear reactors are, for the most part, very quiet places. The hum is the hum of something vast and steady operating beneath the surface of ordinary life. In France, roughly 70% of the electricity comes from nuclear power. In the United States, about 19%. In many countries, somewhere between those numbers. The lights in hospitals, the refrigerators keeping medicines cold, the servers storing the photographs of people we love. A significant fraction of all of that runs on the energy released when slivers of mass in fuel rods, in reactor cores, become something other than mass. The reactors producing that electricity are, in their daily operation, remarkably unremarkable. They sit behind their thick concrete walls and do their slow, controlled work, month after month, year after year. A fuel assembly in a pressurized water reactor is typically replaced every 18 months to 2 years. The fuel pellets that go in are grey and ceramic and look like nothing much. The ones that come out are intensely radioactive and must be handled with great care, but they are also, by then, mostly spent, most of their uranium-235 consumed, most of their energy given up to the water and the steam and the turbine and the grid. New reactor designs are being developed that will make this process still quieter and still safer. Small modular reactors, smaller than conventional plants, designed to be manufactured in factories and assembled on site, are being built and licensed in several countries. Some of them rely on passive safety systems that require no external power and no human intervention to function. If the reactor overheats, the physics itself responds, moderator is lost, the reaction slows, the temperature drops. The reactor cannot run away. It is designed to fail gracefully, to return to a safe state on its own, the way a pendulum returns to rest. Some advanced designs use molten salt as both a coolant and a fuel carrier. The uranium dissolved directly in the liquid salt, which flows through the reactor and then through a heat exchanger. If the reactor overheats, a plug at the bottom of the vessel, kept frozen by active cooling, melts, and the fuel drains by gravity into a subcritical storage tank where it cannot sustain a chain reaction. The safety mechanism is literally a frozen plug of salt melted by the reactor's own excess heat, draining the fuel away from the neutrons. Elegant, patient, designed around the physics rather than against it. And then there are the machines that have already left us behind, that are so far from Earth that the physics of nuclear decay is the only thing keeping them alive. The Voyager probes were launched in 1977, and they are still out there. Voyager 1, as of the mid-2020s, is more than 23 billion kilometers from the Sun, so far that a signal traveling at the speed of light takes more than 20 hours to reach it. At that distance, sunlight is a faint glimmer, far too weak to power a spacecraft. The Voyagers run on radioisotope thermoelectric generators, devices that use the heat produced by the radioactive decay of plutonium-238 to generate electricity directly through a process called the thermoelectric effect, in which a temperature difference between two materials produces a voltage. Plutonium-238 has a half-life of about 88 years. It decays by emitting alpha particles, helium nuclei, and the energy of those particles becomes heat in the surrounding material. The heat flows through a thermoelectric converter and becomes electricity. No moving parts, no chain reaction, no moving parts, no moderator or control rods. Just the slow, steady decay of an unstable nucleus, releasing energy at a rate determined by the half-life, powering two small spacecraft at the edge of the solar system, sending faint signals back across 20 hours of empty space to receivers on Earth. The Voyagers are powered by the same fundamental process that we have been exploring all night, the conversion of nuclear binding energy into heat, driven by the instability of heavy nuclei. The mechanism is different from fission. It is decay rather than splitting, alpha emission rather than a chain reaction. But the underlying physics is the same. The mass of the plutonium-238 is slightly greater than the mass of the products of its decay, and that difference, that sliver, becomes the heat, that becomes the electricity, that becomes the radio signal, that becomes on a screen somewhere in California a blip of data from the edge of the heliosphere. The Voyagers have crossed into interstellar space, the region beyond the Sun's influence, where the solar wind fades and the thin gas of the galaxy begins. They are the most distant human-made objects in existence, and they are kept alive in the dark between the stars by nuclear decay, by the same patient instability that sits in every heavy nucleus, waiting. Somewhere in all of this, in the history of discovery, in the trembling liquid drop, in the curve of binding energy, in the ancient reactors of Gabon, in the December night in California when fusion ignited for the first time, there is a thread that connects everything. How was the one high O? It is the thread of matter offering up a fraction of itself to become something else, not reluctantly, not violently, in the sense of something being forced, but according to deep and ancient rules, rules that were written into the fabric of the universe in the first moments after it began, when matter and energy were still finding their relationship with each other. The universe, in its first few minutes, was a place of fusion. Hydrogen nuclei fused into helium, helium into lithium. The light elements were forged in those first few minutes of extraordinary heat and density, and then the universe expanded and cooled, and the fusion stopped. The heavier elements, carbon, oxygen, iron, uranium, were forged later inside stars over billions of years. When massive stars died, they scattered their contents across space, and some of that material eventually gathered into new stars, new planets, new oceans, new life. The uranium in the fuel pellet in a nuclear reactor was forged in a stellar explosion that predates the Earth. The iron in your blood was forged in a different star, long dead. The hydrogen in the water on your nightstand was made in the first minutes of the universe itself. We are not separate from this story. We are part of it. The body lying in the dark is made of atoms that carry their nuclear histories with them, the half-lives and binding energies and isotopic ratios of processes that happened billions of years ago, in places unimaginably far away. The energy that keeps you warm tonight, that runs the slow processes of breathing and heartbeat and the quiet work of cellular repair that happens while you sleep. That energy is stored. Chemical energy, yes. But the chemical energy is itself a tiny echo of nuclear energy, of the binding energy released in stars and locked into complex molecules over billions of years of chemistry. You are, in a sense, running on ancient light. The food you ate today carries energy that came from the sun, via photosynthesis, via the food chain. The sun's energy came from hydrogen fusing into helium in its core. The hydrogen in the sun is the same hydrogen that was forged in the first minutes of the universe. The energy has been passing through forms, nuclear, electromagnetic, chemical, metabolic, for nearly 14 billion years, and tonight some small fraction of it is keeping you alive in the dark, doing the quiet and necessary work of rest. There is a strange comfort in this, if you let it settle. The universe has been managing these energy transformations for longer than the Earth has existed. The sliver of mass that becomes energy in a reactor core is the same sliver, following the same rules as the mass that becomes light in the sun, or the mass that powers a probe at the edge of the solar system, or the mass that was converted in the stellar furnace that forged the calcium in your bones. Everything is connected, not metaphorically but physically, through the conservation of energy and the equivalence of mass and energy, and the long, patient history of matter in a universe that has been doing this work since the beginning. The nucleus trembles, the neutron arrives, the drop elongates and snaps, the sliver vanishes, the fragments fly, the heat rises, the water boils, the turbine turns, the light comes on, and somewhere in a city, someone who has been awake too long finds the room a little warmer and closes their eyes. The Voyagers are still out there, still sending their faint signals home, still powered by the slow decay of plutonium in the dark between the stars. The Oklo reactors ran for 300,000 years and left their products locked in the rock, barely moved, patient as geology. The binding energy curve arcs from hydrogen to iron to uranium, and the energy available in that arc has been there since the beginning, waiting for nuclei to find their way toward the stable middle. You do not need to hold any of this. It will be here when you wake. The physics will not have changed. The curve will still arc the same way. The sun will still be fusing hydrogen in its core. The sliver of mass will still be becoming energy in reactor cores and stellar interiors, and the slow decay of atoms in ancient rock. For now, all of that can go on without you. The universe is very good at this. It has had a long time to practice. Let the words go. Let the images dissolve, the liquid drop, the flying fragments, the steam rising from the cooling towers in the grey morning air, the faint signal from the edge of the solar system. Let them drift, the way all things drift when the mind finally releases them. The day is already distant. The science is already settling into something quieter than knowledge, into the particular peace that comes from understanding something true about the world you live in. Drift now, if you are ready. Sleep well.